Hello and welcome to the Penguin Prof channel. Today I want to show you twitch, summation, and tetanus. So here's the big picture. We're talking about the communication between a somatic motor neuron and a skeletal muscle fiber. Okay, so quiz yourself, see if you can identify the parts. And here we go. So we've got a somatic motor neuron shown here, and then leading out of it, that signal travels down the axon. The actual junction between the somatic motor neuron and the muscle cell is called a neuromuscular junction. And that's where the events of today's video will be taking place. So here's a close-up. We're looking at the axon terminal, which is actually expanded into what's called a synaptic end bulb. So it's kind of enlarged at the end. And here we have vesicles filled with the neurotransmitter acetylcholine. And when this somatic motor neuron fires, when it has an action potential, the acetylcholine is exocytosed. I call it cell barfing. Those molecules go out into the synapse or the synaptic cleft, and it's then available to bind to receptors on the skeletal muscle cell. Now, when we compare twitch, summation, and tetanus, what we're actually talking about is the speed at which that somatic motor neuron communicates with this skeletal muscle cell. This is how we look at it. We're going to graph muscle tension on the Y against time in milliseconds. I'm going to use this yellow triangle to show when that somatic motor neuron fires, meaning when this occurs, okay, when the action potential happens. So when you hit this skeletal muscle cell with an action potential, immediately what happens is nothing, okay? It's a latent or a lag period. During that time, actually, a lot of things are happening, right? Acetylcholine is being released, the muscle cell membrane depolarizes, calcium is released from the SR. It's a whole cascade, okay? It's called excitation-contraction coupling. You may need to study this at some point, maybe soon. And yes, I do have a video about those events. By the way, if you find my videos helpful, can you please take a second, use your finger or your mouse and click something below? It really helps me out. It feeds the algorithm and allows me to keep making videos like this for you. Thanks. The next thing that happens is what we call the period of contraction. And this is when calcium binds to the regulatory protein troponin, and you get this whole sliding filament theory story, which once again you may have already studied or it's coming soon. And the sarcomere, the unit of contraction, shortens. Now, if nothing else happens, then the muscle will immediately return to rest. So this is a very fast event, as you can see, and we call this whole thing a twitch. Now, if you hit the skeletal muscle again, maybe 150 milliseconds later, with another action potential, you're going to get another twitch. And a couple hundred milliseconds later, if you hit it again, you get another twitch. How useful are all of these twitches? I mean, are you twitching right now? Actually, you are. The only thing that really relies on muscle twitches is the blink of our eyes. So what if the somatic motor neuron fires and the muscle cell contracts, but if you hit it again right before it starts to relax, you can keep it from relaxing. And actually, the muscle tension will increase. And if you hit it again, you get the same thing. And finally, if you stop stimulating it, of course, it will relax. So what we're doing is actually summing the effects of those action potentials together. The skeletal muscle cell is not allowed to relax. It's like an interruption. So here's a visualization for you. If you want to keep this ping pong ball up in the air, so if you visualize the level that the ping pong ball can hold, what do you have to do, right? You have to keep applying that energy, pushing up from the paddle. So we're getting close, but we need a strong, sustained contraction to do all of the physical things that we want to do. So what if we took this to the final step? So the somatic motor neuron can actually increase its speed even more. If it fires continuously, the muscle cell has no time to relax. The tension remains steady and smooth and strong. And this is called tetanus. This is how our skeletal muscles contract most of the time. So tetanus occurs when the somatic motor neuron fires basically continuously, okay? Calcium levels stay high The power strokes continue, muscle tension is maintained, and this is how you do things like dance and walk and lift weights and do all of the things that you rely on your skeletal muscles to do. And this will occur until the somatic motor neuron stops firing. And then the muscle cell, of course, will relax. Now, I know what you're thinking. Tetanus reminds you of something else. There is also a disease with the same name. So don't be confused by that. Tetanus is a very serious condition. It results in severe muscle spasms, usually beginning in the jaw, which is where it gets the street name lockjaw. Symptoms can last for weeks or months. We see generally a 10% lethality, and it is all prevented by the tetanus vaccine. So in summary, a single action potential from one somatic motor neuron results in a skeletal muscle twitch, which includes a latent period, a period of contraction, and a period of relaxation. If the somatic neuron fires multiple times and interrupts the period of relaxation, the tension can increase, and the muscle cell will not relax until the somatic motor neuron stops firing. In typical skeletal muscle contraction events, the somatic motor neuron fires continuously, and this results in smooth, steady, what we call tetanic muscle contraction. And if you're ready for more, I'm going to recommend this video to learn even more about the amazing world of skeletal muscles. As always, I hope that was helpful. Thank you so much for visiting the Penguin Prof channel. Please show your support by clicking those buttons below, and I will see you in the next one. Good luck.